So this is another example dealing with equivalent resistance, but this one's taking a little different approach. So in this example, we're given the mesh network shown there, but then we're also given these voltage relationships between these nodes. And so they're asking us to calculate the equivalent resistance seen by the current source. So here's the current source here. So it would be between these nodes B and D. So, if we were to take the current source out and put an ohm meter there, what would be the resistance we would measure? Now we could try to, untangle this mesh of resistors and work backwards and do that. But with the information given, there really is an easier way to do this. And so let's take a look at that. So, we need to keep in mind that, we look at Ohm's law, V equals IR, that we can solve for R, which gives us R is equal to V over I. So in this case, we know the I, right? That's been given to us. That's 3 amps. So if we could determine the voltage difference between B and D, then we could solve for that resistance. And that's probably a cleaner, easier way to do that. So let's see how we do that. So again, the points of interest are to find the voltage drop or voltage drop between B and D. Well, they don't give us that over here in this list, but they do give us 2 connecting points to that. So they give us the voltage drop VBC, and they give us the voltage drop from VDC. So we should be able to take that information and determine what the voltage distance or difference is between those 2 nodes. So let's look at that. So if we first look at between B and C, that means the voltage between B and C then is equal to 3.5 volts, and that's given right there. Okay, so now we want to again look at this, but we're going to go now from C to D. So we need to find what VCD is. Well, we don't have VCD, but we have VDC. So in that case, it should be the minus of that, which should be equal to minus 3.125, or just 3.125. Okay. So now, if we look at our equation again, if we go back to looking for the equivalent resistance, that's going to be equal to VBD over our current source I. Well, VBD is going to be VBC plus VCD. So that gets us all the way around the loop here, right? And then again, our current source is the same. So when we plug these values in, our VBC we said was 3.5 volts. And then that's going to be plus our VCD, which is 3.125 volts. And that's all of our current source, which is given in the mesh diagram of 3. And so then that will give us 6.625 over 3, which means our equivalent resistance is, if we plug that in the calculator, we should get 2.208 ohms. So again, if we were to take the current source out and then measure, put our probes at these 2 nodes and measure, we should measure 2.208 ohms. Okay. So now there's another part to this problem. Now they want to know what is the total power absorbed by the current source. So that's easy enough. We know that power is equal to voltage times current, right? So in this case, we know the voltage. We calculated that right here. It's VBD. So VBD and times our current, which is our current source. So this should be 6.625 times 3. Plug that in the calculator, and that should give us 19.88 watts. So that's the answer to part 2 of this equation. So the equivalent resistance is 2.208, and the power absorbed by the current source is 19.88 watts.